can't look at the row right now because it's been mass confusion around here.
This on Blackboard, Mr. Rich? What you showing right here?
This is actually RS Logic 500. What I've done is I've printed these off. And of course, the way the programs are set up with four subroutines in one main program. So usually when we set up subroutines, we have one main program, which Alan Bradley calls ladder 2, right? I call that ladder 2. If you don't, it's still called ladder 2, even if you give it another name. Except what happens is when the subroutines load up. So when you originally load up one of Alan Bradley programs using RS Logic 500, and I imagine it's the same way on 1000 and 5000. So here's our ladder. So file 0 and 1, these are reserved for the system. And we start with ladder 2, right? So ladder 2 would be the main program. Then we have the ability to give it a name. How do we give it a name? Now we just right click on the name and then choose rename, and then it allows you to give it a name. By default, it's called ladder 2. So what you can do now is you can give it a name that kind of specifies basically what that routine does. And they call this origin. And what we're going to do on the Siemens PLCs, when we set up the subroutine, we're going to give them the same name that Alan Bradley uses, which makes sense. So it'll make it a lot easier for us to see it. And I'll show you how to get the subroutine name. But these are the subroutines, but the subroutines don't. The only one, the original one that pops up is, of course, it's 4. And then you come down through here, and then you would just double click on these, and these would bring up the subroutines. And then this adds different tabs down in the bottom that shows you the different subroutines. And then, of course, now we can come up and we can look and see what these subroutines do. Now, what they've done is they put comments about they put comments above every rung. Unfortunately, well, it's not unfortunately. Festo is a German company. So this one I've tried to go in and change, but it took so long. So what they first start off with is they start off with what? German, and then they fall down into English down here somewhere. So this is actually this. What you need to do when you put your comments is you need to start it off with this. So that would actually be the title, S1 colon, and then this would actually be the name we would use. So instead of using that thing right there, this is the English name for that rung, right? Does that make sense? Is everybody okay? And then when you get to your comment, you would just, and this would be the comment that we would actually write down that would tell us basically what this rung is designed to do. Does that make sense? Now, Alan Bradley, puts their symbol names in green, right? PLCs stop using the name symbols. They start calling these tags. Okay. So what we'll do is we'll use exactly the same tags that they use. So we're not going to write the program. We're going to convert the program. Does that make sense? Because we don't have time to go over there and figure out everything that happens. So all we're going to do is take a program this program that was written for the RS Logic 500 and convert it over to step 7, what they call TIA portal package is what we're going to do. But they're very similar to one another. All we got to do is, so inside the step 7, it has the same commands. We just got to figure out which ones are the appropriate, because it's just like on robots, they all do the same thing, but for some reason they call the command something a little different. So that's what you got to do is figure out what command in there. Of course, this is where I'll come into play, because that takes a lot of work. So these are the 4 subroutines One of them they call Otto, which is the main, that's the guy. This is the guy that takes care of that session. And this is where you understand these internal relays, these internal coils, we call them. Because when you get into a complicated control system, 90% of the relays are nothing in there but for decision making. That's all they're in there. And so what we do in real life, it was motor controls, all those control relays, you have to wire them up. But none of their contacts ever leave the control circuit. None of them go into the power circuit. Okay. So normally when we get into electrical control diagrams, we have a control circuit, which is nothing but the control, and then we have a power circuit, which is where all your motors and all your light, most of your lights. So a lot of your lights, since they pull so little current, those might even be inside your control circuit. But your power circuit, your motors and stuff like that, they would be over in another diagram. So all we've got to do is any decision making coil that does decision making, we're going to use internal bits, right? You understand what we call internal relays. So this is what I was talking about. These are the rungs. This is just decision making. Looking at all these sensors. So this says, okay, is it it's something called toggle? Is the line in its, is that module in its initial position? Then it's in step one, which is, this is step one, and we'll come back and clear it out. And was the reset okay? And then it just falls down through all these. Something that we didn't get an opportunity to do, and we should, this should be made sure we do this in the intro to this too, is use an internal bit we call a latching. So what we do is we teach how to do a seal-in circuit, right? You understand? So we could do this with seal-in circuits, but it would be extremely complex because it's going to take one condition to seal it in and another condition to drop it out. Understand that? So what it's easier to do with what we call latching relays. So what you do is right here we got a latching relay. It's using an internal bit, B0/4, right? B30-4. And this is going to latch it. And once it's latched, how long is it going to stay latched? Until you have another coil that has the same address that you tell it to do what? Unlatch it. Does that make sense? So here what we're going to do is, as soon as this is true, we're going to unlatch this thing, right? You understand? We're going to latch this into this one. And then it falls down, and you see it's pretty standard. Latch, and then the center is going to be a what? Unlatch. And all these guys are just decision making. All this is just determine if it's in this position, if this sensor's true, if this step has been completed successfully, and all that. And this goes all the way down. Decision making goes down all the way down until rung. So just think about the relay in relay logic and motor controls. How many dang relays would be required to do this? So we're going down through here, step 13, 14, 15, 16, 17, 18, 19, 20. This is still decision making. And we're all the way down here, this is where we actually generate outputs. I went a little too far. So on this one, the decision making is over. Everything's okay. And then this is going to come out, and this is where we actually output in here, right? So this is going to do something. This is going to turn on a motor. This is going to turn on a light. But all of the decisions have been made. All the decisions been made. So this guy, if we finally get down to step 11, right, you understand, then this guy's going to go true. Now what does that do? Well, this is going to eject the cylinder, pushing out the workpiece, and that's why it's important that we put these labels, because if we do have problems with our program because we got something, the wrong syntax, we can go to these rungs and figure out which one it's supposed to be, right? You understand? So that's why comments are pretty important. So these are outputs. So of all this, there's only 1, 2, 3, 4, 5, 6, 7 rungs, 8 rungs, 9 rungs that deal with outputs. But most of them are just duplicate rungs. I mean, duplicate outputs. So back there, yeah, but one of them is latch condition, and one would be an unlatched condition, right? You understand? So instead of me trying to come in and figure out what makes the rung true and then what makes the rung false down in that sealing circuit. So when we did, yes, I tried to call Jamie, but she's with one relay is everything that would make the rung true, we would put inside this guy, right? Understand? And then what was made to make the rung false, we would put inside the sealing circuit. So if it would, so what would make it true would seal it right, you understand, and then what would make it false would drop it out. So we could do this, but it would become very complicated. So it's actually easier to program it to have one rung that does what? Latches it, and one rung to do what? Unlatch it. And that way you can divide this. So what's required to latch it, you would put all that in one rung by itself, and what's required to unlatch it, you would put that in the other one, right? That makes sense. So what would unlatch this? Either this is true or, I'm sorry, either this is true or this is true or this is true. And now we don't have to figure out if we want to use a normally open or a normally closed, right? It makes sense. So all we're saying, okay, if any one of these are true, because that's ORed, right? And it's going to do what? It's going to unlatch that output. So we have, so inside the step 7, we have latching and unlatching. Unfortunately, they don't call it latching and unlatching. They call it set and reset. Alan Bradley used the term we use for these relays that we use in motor controls. We have what we call a latching relay. And a latching relay has 2 coils on it. One of them does what? Latches it, and the other coil unlatches it. And we call them latching relays. Siemens took the path of digital. So digital calls them sets and resets. So, but it's very, very the same. And we'll look at that, the difference, a little bit in here. So you okay? So first thing we'll do is figure out how to set up subroutines. And this guy's a little hard. Siemens is really cool. The way we set up subroutines, how we call subroutines. So here we call them by, oops, let me go back. So all the main loop does is just basically do what? Jump to 17, takes care of E-stop. Jump subroutine. And then it does some stuff that handles reset and stuff like that. And what we're going to find out is that these routines are basically the same on every module. The one that varies is what? Auto. That's the one that handles the module. But every one of them has a reset button. None of them right now have an E-stop button, but we're going to add that. We're going to add that ability when we convert it over. So we can actually see what happens when we have an E-stop. Are we okay? There he is. We just don't talk about him again. Well, I like early classes because I don't have to stay. I do. Yeah, it's much better getting out at 1:30, and we have to talk about that too. So this class goes to 1 hour. This class runs to 1:30 because it's a 5 contact hour class. And I think Milton asked about it. You asked that about that yesterday. Why does sensors get out at 12:30 and this class goes to 1:30? Because this class is a lab-based class. It has more lab than theory. The other class has more what? Theory than lab. You'll award contact time depending on the layout of the class. So every hour of lab we have to meet the class 2 hours. Every credit hour that's assigned to lab we have to meet at 2 hours. Every credit hour that's assigned to theory we meet at 1 hour. So this is what we call this is a 3 contact. So this is a 1-2. So that's 1 hour granted for theory, and 2 credit hours granted for lab. So every credit hour given to lab has to meet 2 hours. Does that make sense? What do you mean what to do about it? Yeah, we're okay. We'll just split the difference by 15 minutes. So Hoyt won't start his class. He'll start his class 15 minutes late. So we're okay so far. So we'll see how to set up subroutines. It's a little different on the step 7. In fact, it's a little easier on step 7 to me. Then we'll have to figure out how to set up tags. We'll look at different methods that we can use to set up tags. One way you can do is you can actually set up the tag. Like in this situation, what we can do is we can go ahead and look at all these. And I've set up a table. I'm going to print this out for y'all, where you can document your tags right off the bat. And then what you can do is you can set up your tags before you even start your program. And then from then on, when you write your program, you're not dealing with addresses anymore. You're dealing with what? Names. And you can see these names pop up all the time, several times inside the program. So subroutines, everybody I know Jobert hadn't had that, but subroutines, but he understood it pretty well. But y'all understand that. So what do subroutines do for us? Well, that's a point, and that's true. But the main advantage of subroutines, it gives us the ability to divide the program up into modules. Each module has a task. So if I have problems with a task, I don't have to go into a program and look through 500 runs. I go to the subroutine that handles that task. Does that make sense? So what we can do now is that we can do what? And all I have to do, if I want to troubleshoot just that module, all I have to do is just come over here and put a line in here that takes away that return. And then now my program is just going to scan that module, right? And I can play around with that module as long as I want to and get it working what? Right. And then put the return back in there, and then it'll work as a subroutine instead of a module. So what a subroutine does, it allows us to take long programs and divide it into modules. And each module does what? Performs a certain task inside that program. So it makes the program easier to troubleshoot. It makes it easier to figure out how it works, right? You understand that? So instead of me trying to go through everything, I can figure out how each subroutine works. It makes it a lot easier to edit if we do have a problem, because it's real easy to identify where that problem occurs, right? So it's real easy. Instead of me trying to find that into a 500 run program, what can I do? I can go to the module that handles that and see if I've got any problems there. That makes sense. So subroutines are really neat. This is called structured programming, guys, and structured programming gives us the ability to edit the program a lot easier to troubleshoot. So that's RSLogic 500. The TIA software stands for Total Integrate. TIA. This is the newest version of Siemens programming application, and they call it Total Integrated Automation. So used to, like with Alan Bradley, you have to run different things depending on like RS Linux. So when you first establish the communication with the PLC, you have to run RS Linux and establish a driver and all that other kind of stuff. If you're going to use IP addresses, you got to run another program called DHCP server. You got to run that to assign an IP address to the PLC. If you want to program an HMI panel, you have to have an application to program the HMI panel and then match the HMI panel to the what? To the PLC. Well, what they've done is they took every bit of that. Every bit of that is inside this one software package now. So the ability to program HMI, the ability to assign IP addresses, the ability to do all that is inside one application. So instead of me trying to run all these different applications, everything is where? All here now. We're going to have to install it on these computers, by the way. We'll have to figure out if it's going to work. I think when I ask y'all to install, it's going to ask you for administrative password, and I'll have to enter that in for you. So we call it Project View. They call it Project Tree. So I just loaded in a program. And here's everything. So right off the bat, the first option I got is to do configure device. We'll come up here. It'll ask me if I want to add a device. If I say add a device, it'll ask me the information about that device. They've added another feature, which is really, really cool. I'll have to show you that. So what we'll have to do is, normally what we do is we get the PLC, we look on the side of it, we get the model number, and we get the actual, that big long, like how many character model number you'd have to figure out. And then we'd have to select that. I've already got a program, I've already got a program in there, but, I needed to put new, but anyway, we'll go ahead, since we looked at that, we'll look at the layout of, this program. So this is the distribution section. This is the one that I wrote. And so they call it this is the project tree over here. Okay.
So we're looking at essentially like the art project.
Yeah. This is the Siemens version. What we would do here is we'd go here, so this is the PLC that we're using. I'm going to click on that. And then I'm going to go to program blocks. Oops. And here's the program blocks. They call their main program OB1. So they call theirs an object block program. They call it OB1. So ladder 2 and OB1 are exactly the same thing. I'm going to come up here and double click on that, and this is OB1. So this is the main program. Or the main module of a structured program. And these are the other subroutines. Now you'll notice I've given them the exact same name as the one that Allen Bradley. So this is it, guys. I mean, this is it. The subroutine is kind of calling the subroutines a little different. On Allen Bradley, they put it over here, but for some reason on Siemens, they put it right there. They don't call them rungs. They call them what? Network. And the run, huh? That one. And they don't connect the networks together, which is pretty strange. So this would be different rungs in a ladder diagram, and they don't draw L2. They don't draw L2. They do draw L1, but they don't draw L2. So they know L2's got to be over there, right? Understand that? Yeah, they assume. And then they come up and they don't connect the networks together. So these are all part of the same program. You know what I mean? Oh, I think Doug Jones is coming in today. No. Isn't Doug Jones coming over today? The third? I was just wondering. I thought that's what you might be here for.
No, I'm not.
Yeah, I do. So notice that it's open one, and what I need to do is come up here. If I wanted to see all of them, just come up here and double click on them, and it adds another tab down here at the bottom. See it? Huh? Yeah. These are different blocks. These are called function control blocks. And they don't call them subroutines. They call them control blocks. So what Siemens does, all their programs are called blocks, right? You understand? And this is a function block. So it's not the main program. It's a what? It's a function block. And they put them in alphabetical order. So what I usually do is just come out here and put them in the right order and open them up in the right order. Okay. So now if I wanted to go to any of the subroutines, I just come down here and pick up the tab. So So this is like OR, and this is,
The road shows the double blue line. Does that mean it's waiting for-
no, that's just the line that's been selected. What do you mean?
Okay, that's.
Say when I put my mouse, huh?
Turn the wrong, it's like double blue line on.
Like that, that means that's where, that means that's why I'm, so if I was going to insert another item into that rung, that's where it would go. It would go in that place. Okay.
And essentially when you do insert, it's right there above. a little,
Well, it's going to go in here. It's not going to go, so if I wanted to put something here, I'd click, right? You understand that?
like you wanted to turn that into one of those.
Well, here we wouldn't have to do that. It would notice it's kind of like Siemens. I mean, it's kind of like RS Logic. When I click on there, there's a little right arrow up there, and then I can drop it down. Now, what you have to do on RS Logic is you have to retype it. So if you're using examine if open, you have to type in, you have to put examine if closed. What this does is this shows you the different contacts that's available right there. So now all you have to do if you wanted to change it is just select the other contact, which is pretty neat. And also, this is your quick access bar right here. All your instructions. So instead of using the little scroll across the top, what Siemens does is put all the commands over here. So I'll come up here and here's my arrow. I'm gonna click on that, and then this pops out all your commands over there. By default, you get a normally open, a normally closed. You get a coil, which you either make an internal or an external depending on the address, right? This is the down drop, which would give you one of these. This is the up, this would give you one of these. But what you can do is you've got all this space right here to add whatever you want to up there. So by default, set and reset is not up there. But all you have to do is once you find it inside the bid instructions, whatever you want to add, you just drag it. Y'all know how to drag in Windows, right? You just hold it and then drag it over there. So what I've added to my quick access menu is I've added set and reset because that's all over the place, right? You understand?
So you make your own access bar.
You make your own access bar. And this guy, I'm still playing around with this block right here. You can make that thing almost anything you want to. It's pretty neat. But I'm still working on that one, so we'll ignore that. So don't delete it. I think you can right click on it and remove the instruction. Now you're not deleting the instruction. You're just taking it off your quick access bar. You know, so if you get a bunch of instructions up there that you're not using. So a lot of people see an instruction and they put it up there and then they realize they only had to use it once. So if you want to get rid of one on your quick access bar, you just right click and then choose what? Remove. So any of these instructions, so here's your bid instructions, your timer instructions, your counters, your math, your comparators, your move operations, your conversion, which would be like ours, binary to BCD and that kind of stuff. Program and control, so this would be your subroutines and your jumps. And I don't know what word like it, and then your shift and rotate. So that's basically, this, to me, and it's a little easier to get to than the way they do in step 7. But it's still basically the same. So you'd figure out the bit, you'd click on the little arrow, it'll pop down, and this shows you all the bit instructions that's available to you. Are you okay? All that makes sense?
Mr. Rich, so clarification, you said the Siemens subroutines are called a block.
Yeah. So OB1, that's an origin block. FC is function blocks. Those are your subroutines. We'll show you how to do that. So you have to add a function block. Well, it's not real hard. You know, right here below your program blocks, the first thing you see is what? Add a block.
So in here, we were on Siemens. Would you call it subroutine or would you call it blocks?
Well, we call it subroutines is what it is. It's just that they call theirs. It's just even RS Logics don't call theirs subroutines. Well, I'm sorry, they use a jump subroutine. Here, the subroutines. So let's go back. So here, what we're going to do is once we establish a block, which is pretty neat, once we establish a block name, then we just jump to that block. Well, that's all we have to do. So we don't have to remember a U number. right? You understand? So back in Allen Bradley's, I drop it down. You would have to remember the file number that you assigned that subroutine. So your JSR doesn't use a name for RS Logic. You specify a file number that it's supposed to jump to. And what they do in Siemens is you just give it the same name. In fact, guys, all you have to do to jump to subroutine is you set up your rung, you come up here, you grab the subroutine you want to come to, and you drag it and put it on there. That's all you have to do. And once you give the subroutine a name, yeah, to use it. So you don't even have to enter that instruction. If you find a JSR, there's no JSR instruction in the palette. Because how do you add a subroutine? Well, once you get the rung out there, all you have to do is just come over here and find the subroutine. You left click on it. Y'all know how to drag, right? And just drag it onto the rung. That's all you have to do. So you can look all day inside the program control instructions if there's no JSR instruction in there. So you don't have to remember the U number. You don't have to do anything once you set up the block, right? You understand that? Which is pretty neat. So I gave y'all the secret. So it's real hard to do. So what you do is you just go ahead and add a new block, right? You understand that. How do you do that? Click add block. And then you come up and you just assign it a name. And in the programming language, so the two programming languages available, so these are the three programming languages available. Now we don't teach function block programming. So function block programming is when you program with symbols, right? You understand that. So you have a symbol for an and, you have a symbol for or. So this would be for people who came up through digital. So basically digital, when you do digital schematics, you just learn a bunch of symbols for ands and ors and nots and nors. Well here, that's what you do. Function block programming, that's what you program it. SCL, that's text language. That's a text programming language. So that means people that came up through writing programs like in these programming languages, C and Visual Basic and all those, they would understand how to program that. This is where we come up through. We come up through, through motor controls and stuff like that. So our prominent language is ladder. So by default, it's going to give you ladder, but you could program in each one of those. You give it a name and you hit what? Okay. You just created a program. Yeah, each one of those has a different function. We can establish different data areas for different types of data. So if I'm using a lot of word data, instead of me specifying a word every time, I could set up a function block for that. If we're using arrays or tables that we go through, we can we can dedicate a section of memory toward that. It'll automatically set up a data block for anything that needs data blocks. So data blocks are for devices that need more than 1 byte, right? You understand our byte of memory. So what some of the devices that we looked at in RS Logics that needed more than 1 byte of memory? What devices? One of them starts with a T. Timers, right? So anytime you use a timer, you don't have to set up a data block. It'll automatically set up a data block for that timer. So it'll reserve so many bytes of memory for that timer. Counters need more than 1 data block, right? So more than 1 byte of memory. So some of them automatically assign them data blocks. Some of them don't. Subroutines, you can look these up if you want to. We don't need to do that. All we have to do is come up here and type in a name, and then come down here and click Alt what. Okay. That makes sense. So that's a really good question. Some of them are data blocks that can be shared between multiple PLCs. Some of them are data blocks we call them global data blocks. Some of them are not global, or I'm trying to get the word out. I guess you call them local data blocks that can't be shared across the network. Are we okay? So I set up 1 data block just for the heck of it. I don't even need it. But if we was going to establish what we call an array, y'all know what an array is? An array is a table. So an array of stuff where we store information at that we're going to use a lot. So instead of me trying to go out there and pick it up, so an example, would be a code that I'm trying to convert to. Well, instead of my computer trying to remember the code, instead of me trying to remember the code every time, I could set it up in a memory, in a table, right? And then I could go in and look it up in the table. That makes sense? So like a phone book. A phone book is a table. So you're setting up a table when you set up a contact. So now instead of you trying to remember somebody's phone number, you can tell your phone to go inside that table, right? And it gives you the phone number, right? You understand? So we're constantly doing that where we're trying to match this information over to another type of information. So any type of something, anything like that I have to go up and look up things, like I said, your contact list, then you're telling your phone to set up a what? A table. And then what information do you put in your contact list? What information can you put in your contact list? Your name and number. What else information can you put in that contact list? Email address, right? So what you're doing is you're not only setting up a table, but I'm trying to find something. So an array can be 2 dimensions, or it can be multiple dimensions, right? You understand that? So what we have to do is set up the ability to go into that table and pick out what we're interested in. Now, a lot of times this is totally transparent to you. So you bring up a contact, and what information does it bring up? It brings up, what information does it bring up? It brings up their email address, right? It brings up their name. It might bring up their fact. Yeah. So if I come into to here, on the email accounts usually have a lot more information, especially output that you can enter into the thing, right? So what else? What can we enter into this contact? Oh yeah, we got all this address, their complete address, their title, their company, their office in, their offices in. Do they have an administrative assistant, right? Understand that. If they belong to any organizations, right? Phone numbers, multiple phone numbers, member of, email, different email addresses. So this is what we're doing is we're setting up an array. But the array not only has one match to another, it's actually got depth to it, right? You understand that, which is pretty neat. So that's what we can do with those data blocks is we can establish these arrays. But some devices automatically generate data blocks for you, right? What are those? Those are your counters. I'm sorry, those generate function blocks for you. So everybody knows what an array is. So what is an array or a table? What's an array? Huh? It's a place we can go to look up different information on an item. That's all it is. And you see tables all the time, right? Phone books, contact lists. And if we have to deal with tables all the time, then we need to have the PLC needs to have the ability to do what? To deal with tables. So this guy here uses, instead of using latch and unlatch, what does it use? What does it use? Set and reset. But notice what I've done. This is not part of the original quick access palette, so what did I do? I just drug them over there, right? You can see that I use these things extensively. And what I've done is I've gave these things the same tags. So these are the tags. So all that's here too. So down here, we can go down here, right here. And we got, what's this guy here right here? Field tag data. And we can go to, PLC tags on thing. PLC tags. and then we can go to the default tag table. And I've got this right here's got 109 tags in it. Now, why this has so many more tags is that I had to come in and add things for my HMI panel. So y'all won't have this many tags. Another thing that I like about Siemens is that we don't have a specified data files. So in Siemens, what specified data files do we have? Dedicated data files. What do we have? No, for RS Logic. Sorry, y'all don't know Siemens. What's the dedicated data files we have? Yeah, we have S4. We have C5. We have, and we have F8. We have N7. We have what else? We have T4. Whatever. We have L. Can't remember what L is, but it's for a long word for the 1100s. So these are all dedicated data files. What they decided to do in Siemens is nothing's dedicated. If you're going to use a memory, then you'll start off with M. That specifies a what? Memory. Well, no, it specifies a memory. And we got different things. We can put MB. This would identify what? Memory byte. We could put MW. What would that indicate? So, yeah, word. That makes sense? If you don't put anything, it means if we don't put anything, this is a what? A bit. And then we assign a byte number. So this is one big difference. One big difference with Allen Bradley's RS Logic 500s and Siemens is that the minimum data file that we can have is 16 bits. So what we'd want to do if I wanted to set, and so B3, that's a dedicated word. So one thing, Siemens has no dedicated, it's memory. And we decide what goes where, right? You understand that? So we don't have a bit dedicated to AFA. We don't have a bit dedicated to this. We specify the length that we're dealing with by the way we address the memory. So everything starts with M. Then what do they do in Allen Bradley? They put a colon up there. And then what do we put? Then we put a byte number, right, inside that data file, like 4. And then we do what? Put a slash, and then we dedicate a what? A bit. So this would be the byte number, not the byte number. This would be the word number. I got them backwards. And then this would be a bit inside the word. Bit. So this is where we're going to get into a little trouble in that what they do is since we have no dedicated data files, we start off with M, and then we come up here and we put a byte number. So that's a 0. There's no such thing as an O. So M, once you enter M, you're through with letters. Or once you enter MW, you're through with letters. Now you're switching over to what? Numbers. So I'll put this. That's an O computer, meaning that's what. Now, what the main difference, instead of sacrificing all this memory, so if I wanted to use 1 bit on the RS Logics, I would have to sacrifice a whole word of memory. Right? You understand that? For 1 bit address inside there. What we do in Siemens is Siemens don't use bits. Byte words. They use what? They use bytes. They use a byte. Everybody know bytes and bits, right? Then what we do, and this is the big difference, we put a period, and then we put a bit number. So the same address down here would be, this would be byte 4, would be like M something, right? Down here would probably be M8 slash, not slash. You got me. I was just making sure. M8 and this is what's going to be hard coming directly from the Allen Bradley, M8, no colon, dot 2. So if I was going down the sequence, these guys would be pretty close to an equivalent address. So while over here I use 4, over here in the Siemens I use what? 8. Why? Because there's 2 bytes per word. Everybody understand that? Yes or no? So that's what we're going to do, is we're going to come up here and take these addresses, like if they're doing B3, 0/1. Well, what we're doing is we're converting an Allen Bradley program over to a Siemens program. Allen Bradley deals with words. So they'll come over here, they'll have a B3, let's say 0/1, B3 0/2, B3 0/4, B3 0/5, B3 0/6, B3 0/7, B3 0/8, right? And I keep going, B3 0/9. Now we're going to convert this over to so let's start off over here. I'd start over here, I'd say M0 dot, I left that one by the way, B3 0/0. I would start off M0, right, dot 0. Everybody okay there? Okay. Then I would go what? Then I'm going to go M0.1. Then I'm going to go M0.2. Then I'm going to go M0. I've left that one. Yeah, B3 colon dot slash. Okay. I would go 0.3. Then I'd go M0.4. Then I'd go M0.5. Then I would go M0. No, let me keep going. I'd go M0.6, then I'd go M0.7. I'm through with M0. That's a byte. There's no such thing as M0.8. Siemens goes in bytes, Allen Bradley goes in words. So my next one I would use M1.0, which would be that guy right there. My next one I'd use M1.1 and go vice versa, right? You understand? Yes or no? No, because we can't address a bit with a word. We can't address a bit when we're telling it it's a word. When you put MW, it's going to use the whole word. I'm not addressing a bit anymore. Yeah, it's just like when I use F8. When I use F8, I'm specifying 2 words, right? You understand that? So that means if I was to try to use an F8 register for something else, I can't use it, right? You understand? So I can see you're confused. So as soon as I see MW, I'm not working with what anymore. But I cannot add it. So I would say MW0, and that's it. MW0 would take up that whole word, and I cannot address a what anymore. A bit. It's ugly, but anyway. So what we've done is I've set up a chart where you're going to write down Allen Bradley addresses, and then you're going to convert them over to what? Siemens addresses. So then I would go down here when this hits B3 0/15, and then I would use what? I'd be using M1.7. Then it goes to B3, and then they would have to go to the next word, and they'd go to 0. Well, I'm going to go to what? M2.0, because I'm working on the second word, right? You understand that? Which is a little different. So Siemens goes in bytes, right? You understand? Everything. I mean, we use M for everything. There's no such thing as an F8. There's no such thing as an L. There's no such thing. We use M for anything we're doing internal.
So for us, we took
What do you mean?
Like what we do, we were using the counter, we were using the timer or that.
Well, the problem is when you set up a counter, you don't have to do almost anything. You just put a counter in there, and the application takes care of addressing the counter. I mean, everything is basically taken care of for you. So we put a counter in there, and we assign it a tag. And then after that, you don't have to worry about it anymore. And that's what's nice about these high-level programming languages. It takes away a lot of that little mundane stuff that you had to figure out when you was dealing with these other PLCs. It makes sense that, that they would evolve these things and make them easier to use over time. And like I said, originally the only programming language they had available was ladder logic, period, ladder. So that means if you came in from digital, you had to relearn a whole new language, right, to be able to program that thing. So they realized a lot of people was coming into digital, so they added what? They added function block programming. Now these guys can deal with AND gates, OR gates, NOR gates, and hook them together, just like you'll learn in digital if you're in the I don't even think digital is an option in AUT. I'm not sure. Yeah, it's ILT. You actually construct circuits out of these integrated circuits. And then, of course, we got the people coming up through programming in these computer languages, true computer languages like Pascal, which we don't use anymore, But the predominant language now, of course, is what we call C, programming in C. Those guys now, they would have to learn a different language, right? They would have to learn electrical. So basically, these guys can program without almost knowing nothing about the electrical concept at all. So if you went into the computer science program and took C, then you came into this program, that would probably be your what? That would be your preferred method of programming. They got another language this is really cool. I've only played around with it when we was in Germany, but it's where you just take a function chart in programming. So when we convert this over, what I'm going to do is I'm going to give you a chart, a table that you're going to go in, and on one side it's going to have the equivalent Allen-Bradley address, and then you'll just come over and change that over to an M address, right? So what's nice about this language is that it takes away a lot of that mundane stuff that you had to remember, on that. So we're going to use a lot of M's for just about everything, guys. I mean, we're going to use this just a little bit. But once you do this, once you specify a byte, then you have to remember. So if I put M0 right here and use a word, then how many bytes is that going to take up? 16. It's how many bits, it's going to take up. So I'm going to have to remember I cannot use M0 anymore. M0 is what? M0 and M1 is gone. Because M0 and M1 is taken up by that whole word, right? You understand? So that's something that you have to remember. So that's why when I came over here and did that equivalent address, I used a what? I used an 8 because I was in the second byte. And you look at your I/O ports. Your I/O ports are given in bytes. So by the way, they did a little difference too. So inputs are still what? I, right? And if we want to input a bit, we'll come up here and we'll put a 0. That would be for the first byte, right? Understand? And then I'm gonna put a what? Dot, and then I'm gonna put a bit number. Input. So that's the same as Allen-Bradley. Now the problem we have with the Allen-Bradley, it uses it loses the letter O for input. How many of y'all actually hit the wrong key? I used a 0 instead of an O, or an O instead of a 0. Huh? So what they do on Siemens is they call outputs Q. So what we'd use is we'd use Q. If I was going to deal with a bit, I leave everything alone. Then I would put a bit, I would put a word, I would put a byte number, right? And then I would put a dot, and then I would put a what? A bit address. So I can use a QB. What would QB do for me? It would output a whole byte. So all the ports assigned to that byte would change states according to that. And then I got a what? I got a QW. A QW would output 16 outputs at the same time. But we're not going to use those. But we have the ability on this one to use the same thing, right? You understand? But we identify whether we're using bits, whether you're using what? Bytes, or using words. I'd have to go and look at long words, guys. So what's a bit? It's a single binary digit, right? What's a byte? A group of 8 consecutive, right? And what's a word? 16. And then what's a long word?
32.
It's a double word, but also nibbles don't apply. The only place you're going to run into nibbles is in digital. We okay? Or when you get into hexadecimal, I'm sorry. It's easier to understand hexadecimal if you understand nibbles, because each nibble represents a what? A hex character. Did I close that? Where's my TIA portal at? Oh, I'm sorry. It's set up here on these. So you can see this. So, and this is what you're going to have to translate. So these are outputs, right? Q0. So this would be byte 0, bit what? 2. What's that? Your tags? Well, your subroutines are part of a program. So subroutines are not a program. It's a module of a program. So you only have one tag table for the program. So this is the tags for everything that's in there, even the HMI. So I had it HMI. So you have to duplicate a lot for an HMI panel. So if you're using an input off an HMI panel, you got to put a memory contact inside that circuit, right? But it's going to be addressed to the HMI panel. So all these that says HMI, these won't be into yours to start off with. Eventually, hopefully, we have enough time so you can see how you would convert a program over to be able to run off an HMI panel. And what I decided to do, instead of converting it over entirely to an HMI panel, I wanted to be able to run it both ways, manually and with the panel itself. So we have to figure out where to hook these memory contacts up. Of course, Boolean indicates it's a what? This indicates it's a bit, right? Then we have integers. The integers would be, we have to figure out how much that's solved for. And this assigned it a whole what? MW1, so that assigned it a whole word, right? You understand? I didn't do that, it did. So this specifies, this means this is a what? It's a timer. This put a D, so that's a double word, by the way. So this assigned it actually, so that's what the D. So D, Alan Bradley calls it a quad word, long word, double word. So they're using the D there. This was done for me automatically, so I didn't actually have to do that, right? You understand? But I got to be a cognitive that this is already used. And then these are actually internal bits. We'll look at these right off the bat. This guy gives us a memory byte that we can dedicate clock function. So I've decided to use memory 7. We'll show you how to do that. But this is kind of like the S4 file inside the RS Logic, where we have that timing bit we can use. So instead of trying to use those flip-flop timers, which they have here, by the way, we'll substitute that and use these timing bits. What's nice about this though is when you set up an address to use those timing bits, it actually gives you the what? Gives you the speed of it, which is pretty neat. And we'll show y'all some other timing bits that we have, and we have to assign these. Well, that's not true. They automatically use memory byte 0 for the memory timing bits. But the problem is, if we're going to convert it over, it would be too hard for me to take that Allen Bradley that uses bit 0, right? Uses word 0, and me up here using word 3 just to skip over these. So I'll show you how to reassign that. It took me a little while to do that. I'm going to benefit of me. They call this a clock byte. This is assigned to memory byte 7. Then once we get there, we can just choose the what. I can put a contact at memory 7.0 and give it 10 hertz. It would be doing what? Making and breaking at 10 hertz. So, and we'll see. So right here, that's what I've done. So instead of in the original Allen Bradley programs, they use those cross-coupled timers. But instead of that, I just used what? Yeah, memory 7.7, which is a 5.5 hertz clock, to do that, which is pretty neat. So that saves us a lot of time on there. So our emergency flash routine will be a little different. So what this does is this, when you hit an e-stop, it causes the buttons on the front of the thing to flash at you. You won't see it on any of the other modules right now because why? Because they don't have any stop. They don't have any stop on. So okay, so it looks like a bunch of people show up. So we can, how many got? 1, 2, 3, 4, 5, 6, 7. So we got 7. So we'll have to figure out how to do this. What we're going to try to do, our first lab, and I'll run off a lab sheet for the lab, is just to get a feel of what's going on, is we're going to try to run the Festo line manually. So give y'all a little feel. Well, so what we're going to do is go over and watch it. We'll figure out how we're going to divide the groups up. Probably we'll run, that was close. So when you hear that, you know, it's so we're going to run the line manually. Hopefully the power will go out. And try to run it. We'll decide how to divide it up. Now, no matter which team we're going to do it in a team. I guess we'll do 3 stations. So we'll have 1 team with 3 and then 2 teams with 2. Is that okay? So that way somebody don't have to do it by themselves. And what we're going to do is we're going to look and see how we're going now. And I hadn't made the signs yet. I realized this has happened more than once. Is that, let's don't. So we was trying to show the line off the other day, and somebody got in behind it, and what did they do? They tripped over one of the pneumatic cables coming from our manifold back there, and tore the coupler up. Huh? No, you didn't do that. You didn't do that. So you're going to have to be really cognizant. I tried to tape this one down. The problem we have up this one, I could put more cable on there, but I've already taped it all together. So let's try not to go behind the line. If you go behind the line, watch your feet because there's a lot of stuff. I'm going to start putting a trip hazard. I was going to try to find a trip hazard sign, but unfortunately our internet was down. Still is. So if you go behind the line, there's definitely a trip hazard back there, right? Because it's got a bunch of cables and stuff that connects from the manufacturing line over to the manifold. Not only do we have pneumatic tubes back there, we've also got electrical tubes where we have that. You're going to have to go behind the line to actually hook up the manual simulator to the power supply back there, because this guy actually powers up through the PLC, and we're going to through the PLC circuit boards, and we're going to disconnect the PLC.